Hello, my name is Lion King, and here I will go to teach the derivative matrix for better value functions. Uh, this is the section one. Before we are going to the derivative matrix, we are going to introduce multivariable function. There's two types of the multivariable function. Scalar value function, its input is a vector, and then the output is a scalar. Like the projection function is the classic example. Another one is the vector value function. It inputs the vector and then outputs are also a vector, like this function. The next part is the partial derivative. Okay, what is the meaning of the partial derivative? So this is the definition. If the limit this one is exist. So this limit is very familiar. Like the h we can express as the rate of change, and the ei, the vector ei means the unit vector. So I will give you an example like the two-dimensional. So two-dimensional has along to the direction x and y. So if the unit vector is a 1 0, then this limit is expressed as the rate of change along to the x direction. If the unit vector is the 0 1, then this limit is expressed as the rate of change along to the y direction. So we can denote the limit of this limit as this partial derivative, this symbol. So when taking the partial derivative with respect to the si, all other variables are treated as constant, and only si is allowed to be treated as variable. What it means? So I can give you an example. So give you an example about this one. So I define this function. Okay, so I want to find this partial derivative with respect to x. So look at this. So I want to take the derivative of the xyz. So I treat the yz as the constant and x as a variable. So like e power z cosine x squared is similar. So I can get this answer. To take the answer xyz and then take the partial derivative with x is yz. And then this one, we just take the chain rule of take derivative of the cosine x squared only. So we are going to talk about the most important part, derivative matrix, which we can call Jacobian matrix. Assume the open set O and the vector x not in O. Define function f such that the function f has a partial derivative at the point vector x naught. Then the derivative matrix of f at vector x naught is the matrix with the size m times n. So this is the derivative matrix used type. So what it means of the symbol lambda. If m equal to 1, we call it is the gradient of the function f at vector x naught, which is this one. So to memorize this derivative matrix, it seems look like the complicated. So we can see at this. Each row of the Jacobian matrix indicates the gradient vector of one component function fi. So where I is between 1 and n. So I will give you an example. The gradient of a component f1 function is the partial derivative of f1. Take the respect to the s1, s2 until to sn. So how many rows are in this derivative matrix? Totally n, because the number of rows it follows the number of dimensional f. So how about the each column? Each column of Jacobian matrix is the partial derivative of all component functions with respect to one variable sj. So like this one is the second column. So I take uh, the partial derivative of f1, f2 until to fn. I take the partial derivative with respect to s2 only. So how many the columns in the partial derivative in here? Partially n, because we follows the dimensional of open set O. So I will give you an example. Define the function f from three-dimensional to two-dimensional and let the function divide by this. So find the Jacobian matrix of the function f at vector square root of pi 4 0. So the first step is find the Jacobian matrix of the function f x y z. So note that we want to find the gradient of the first component. So it's similar to the previous example. And then the second component, the gradient of the second component is just take the partial derivative respect to x, y, and z, and then we can get this answer. Okay, so the gradient of f1 is this one, and then the gradient of f2 is this one. Take the partial derivative respect to x, y, z. only. And then we combine together and then we obtain this derivative matrix. After that, we evaluate the derivative matrix at the point square root of pi over 0, and then we obtain this answer. We just substitute these three values into this derivative matrix only. After talking about the derivative matrix, we are going to talk about the importance of Jacobian matrix. So the Jacobian matrix is an essential tool for studying differentiability. So this is the definition of differentiability. The function f is differentiable at vector x naught if there exists the linear transformation t such that this limit exists. This limit is equal to vector 0. So here we talk after we learning the Jacobian matrix, we can know the linear transformation T precisely, which is called the derivative matrix uh, vector x naught times vector h. So we want to talking about the theorem 1. The function f is differentiable at vector x naught if and only if the function f has partial derivatives vector x naught, and then this limit exists and equal to 0 vector. If function f has partial derivative at vector x naught, so it implies this one. So we want to prove the right side to left side first, and that is the easy part. So we can choose the linear transformation T is equal to the derivative matrix times vector H. So by definition of differentiability, so the function is differentiable at vector S naught. So using the definition only. So the complexity is the hard part. Assume the function f is differentiable at vector x naught. So there exists the linear transformation T such that equal to matrix A times vector H. And notice that matrix A is equal to the size of the m times n, because this is the f has the direct dimensional of n, and vector h has the dimensional of n. So we need the matrix A with size of n times n, and then equal to this 0 vector. So we take the vector h is equal to scalar value h times unit vector. So this unit vector is from the dimensional n, and then scalar h is the real value exclude 0. So this limit is equal to 0 vector. So by using the definition of limit, and then we can imply this one. And then also note that I substitute the vector h is equal to the scalar h times unit vector. So the norm of unit vector is equal to 1, and then we get the absolute value h. And then this one, I also get this one. And then note that this part is equal to this part because the norm of h is equal to the absolute value h. So therefore, I can prove this one by using the definition of the limit. So I divided a times h times unit vector and divided by h, and then I obtain this one. And then I'm moving this a times unit vector into the right side. So do you familiar this this limit? So this is the definition of partial derivatives. We can show that this is the partial derivative of this f, and is equal to the matrix A times unit vector. So I can say the partial derivative of f is exists at x naught. So since the matrix A is equal to this one, this is the deformation of the matrix A, and then the each matrix A times unit vector, and then I get the partial derivative is the derivative matrix. Therefore, we can prove that this part is equal to the 0 vector. This is the example. We want to prove this limit is equal to 0. So the hint is given. If a function has the continuous partial derivatives at vector x naught, implies the function f is differentiable at vector x naught. So I define this function. So this is similar to the previous example. And then we want to find the gradient of f, so which means this one. So we take the partial derivative respect to x, y, and z, and then we obtain this one. Since polynomial has continuous, and then exponential and cosine sine function has continuous, so we can obtain the function f as continuous partial derivatives at vector x naught. So it implies the function f is differentiable at vector x naught by theorem 1. So I can obtain this limit equal to 0. So we need to find the dot product of this one. So notice that vector h is equal to syz minus origin is equal to this one. So the gradient of f000 is equal to 001. We just substitute the s, y, and z is equal to 0, and then this one. And notice that the partial derivative of f respect to z is equal to 1. So you can obtain this unit vector. And then also, the f0, is equal to 1. So the dot product of the gradient of this f with on origin and with the syz, then we can obtain this z. And then this is the 1. So we can obtain this limit. And then we take the vector from the z, and then we obtain this limit. So besides that, Jacobian matrix can also to compute directional derivatives. So this is the definition. Any non-zero vector B such that we can define the this one is equal to the this one. And then it is the similar to the differential derivative, but here the vector V is not zero. So this is the theorem 2. The function f is differentiable at vector x naught. Then for any non-zero vector V such that this equal to this one, we need to prove this one. So by definition, we know that the directional of vector is equal to this one. And then since f is differentiable at vector x naught, so by theorem 1, we can imply this one. So the vector h is equal to the scalar value h times vector v. As this one goes to 0, and then the scalar value is equal to the 0. I think you can obtain this one. And then using the definition of limit, you can epsilon can be chosen. So I can choose for epsilon divided by the norm of vector v. And then this one and this one, we move to the right side, and then is the norm of vector v is eliminated. So I can imply this one. And then convert to the limit definition, you can prove this one. And then this part, I divided by the h, and then I move to the right side and obtain this one. By definition, I can prove this is the derivative directional according to v, and it equal to this function. So, just for all. Thank you.